So let's talk about units for a little bit. So what are the lovely system of units that most of the world uses that we don't use so commonly in this country? Metric system, sometimes called the SI system, the System International. So with this metric system, you should definitely know some of the base units. So there are 7 of them. You only really got to concern yourself with chemistry for 4. If you take a physics class, you'll definitely get a few more. But length, meters, mass, what's the SI unit? Kilograms, but what do we use more commonly in chemistry? Grams. Just keep in mind, grams is not the SI unit, but it is the one we use more commonly for chemistry. Time, seconds, temperature in Kelvin. Sweet. And you should definitely know how to go back and forth between Celsius and Kelvin. If I'm at 0 degrees Celsius, what's the temperature in Kelvin?
0 degrees at 273.
273 Kelvin. So if you're in Celsius, add 273 to get Kelvin. If you're in Kelvin, subtract 273 to get Celsius. Cool. Some of the derived units. Volume. If you have a volume of a cube, it's length times width times height. And that would be meters times meters times meters if it was all in SI units. And so the unit for a volume, the SI unit, is technically the meters cubed. So however, what do we use more commonly in chemistry? For volume, yeah. We don't use meters cubed too commonly. In physics, we use SI units pretty exclusively, or at least we convert them to them if we're not given there. But for chemistry, we will much more commonly use like liters and milliliters for volume. Energy and work, the joule. We'll see that a little bit later in the semester and definitely in second semester as well, quite a bit. And then finally, pressure. The SI unit for pressure is the Pascal, and we will almost never use the Pascal in this chemistry course. What will we use much more commonly? Much more commonly, when we get to the gas chapter especially, we'll use atmospheres. We might also use torr and millimeters of mercury as well, but atmospheres will by far be the most common. So, but in a physics class, you would definitely use Pascals much more commonly. So now we got a problem. We like using not the metric system in this country. However, in much of the rest of the world, the metric system is used pretty exclusively. So, and I like to think that that's because we're just dumber than everybody else in this country. If you look, unfortunately, you're going to have to know some conversions. The metric system is beautiful. Everything's powers of 10. And whereas you do have to definitely memorize all the little prefixes and what they mean, so, and there's that text box on your handout that kind of shows that. But unfortunately, in this country, you're also going to have to, know some of the common conversions within our own system, like how many inches are in a foot. 12 inches in a foot, things of that sort, 3 feet in a yard. Probably don't have to memorize this, not the worst thing if you did, but 5,280 feet in a mile, so on and so forth. But then you might also have to worry about, well, how do I get from the metric system to the American system, or vice versa, and things of this sort. Those are what I like to call crossover conversions, and those are typically going to be given to you. But you definitely have to be proficient with your metric system. Let's work out a few examples here. So first thing I want to do is convert 1,500 grams to kilograms. So in this case, we're dealing exclusively with the metric system. What units will I need on the bottom here of my conversion factor?
Grams.
And on the top?
Kilograms.
Kilograms. So the way this works, there's 2 ways to do this. You can kind of say that there are 1,000 grams in 1 kilogram. It's one approach. You could go back and say, instead that 1 gram is equal to 10 to the minus 3 kilograms and stuff like that. So there's 2 ways to set this up. And the second one there is not the most common. But when you start dealing with like centimeters and meters, people do it both ways all day long. Your textbook uses only one convention, and I'm going to use that same convention exclusively. I'm not going to do this a different way. And the convention says that you always give the unit that actually has the prefix on the front a 1. That's always the 1. And the one with no prefix is always the power of 10 that prefix that got the 1 means. So in this case, what does kilo actually mean as a power of 10?
Kilo is 10 to the 3rd.
Good. Actually means 10 to the 3rd. And so in this case, our grams cancel. We will get an answer in kilograms. So in this case, 1,500 divided by 10 to the 3rd gets us?
1.5.
Good, 1.5 kilograms. Great. If we worried about sig figs here, how many sig figs in 1,500? 2. And we'll cover sig figs a little bit later, but definitely 2. How many sig figs in 1 kilogram? 1. How many sig figs in 10 to the 3rd grams? 1. Good question. So it turns out in your conversion factors, That's not one sig fig, and that's not one sig fig. In your conversion factors, you are supposed to assume an infinite number of sig figs, as if we know them to infinite precision. So this says 1 kilogram, but you're supposed to pretend it says 1.00000, because there are not just about 10 to the third grams in a kilogram, there are exactly 10 to the third grams in a kilogram. And even some of the other conversion factors we give you, like maybe there's 2.54 centimeters in an inch or something. For your conversion factors, just assume they're known to infinite precision, even though sometimes they're not. But this one actually is infinite precision. So you're going to get the sig figs for your answer from the original number, never from the conversion factor. So we got 2 sig figs here. We should have 2 in our answer. For multiplication division, so the least number of sig figs gets you the sig figs in your answer. Well, he's the only number we're concerned with, 2. So we need 2, and we're already there. Let's do another example, make this harder. We have 3 to 200 meters. We want to convert it to miles. Now, why is this a little more difficult? Switching systems. So we need some sort of crossover conversion, one that gives us an equivalent amount in this metric system with the American system. And which one is supplied in the problem there? Yeah, centimeters to centimeters to what? Yeah, centimeters to inches. 1 inch equals 2.54 centimeters. So if we're trying to get from the metric system to the American system, I got to do it through centimeters, because that's how I get to inches. And so in this case, the first thing I got to do is turn meters into centimeters. And then what will I turn centimeters into with my crossover conversion provided? Awesome. We'll turn that into inches. And then what should I turn inches into? Awesome. And then what will I turn feet into? Good. And so here we're doing some dimensional analysis. Notice I can set up the units completely before ever actually plugging in the numbers. Every conversion factor expresses the same exact quantity in 2 different sets of units. So in this case, which one of these gets the 1? Actually, so in this case, if you use the prefixes provided by both your textbooks and on the text box there, they always give the one with a prefix the number 1, just as we did right here. So, and in this case, what does centi actually mean? 10 to the negative 2. Notice, instead of doing it this way, very commonly, and this is the way I do it personally when I'm on the side, I would say 1 meter is 10 to the 2, 100 centimeters. But this is the standard convention that I'm going to stick with all night long. Cool. What about inches to centimeters? Well, that's the one that's provided. 1 inch is equivalent to 2.54 centimeters. Finally, feet and inches. 1 foot to 12 inches, and feet and miles. That was also provided on your handout. Good, 1 mile, 5,280 feet. And this is definitely where you need your calculator, because I will definitely not be doing this in my head, which means I'm relying on you. Cool, if you're plugging this into your calculator, you can either multiply the denominators all the way across and then divide by that number, or you could put them all in parentheses, or you can divide by each one separately, so on and so forth. 1.988 miles. Now, we got to get correct sig figs here. How many sig figs should this actually have? Yeah, 3200's got 2 sig figs, so if we round this to 2 sig figs, awesome. We're going to have to round it to this guy rounds up, which actually turns it into 2.0 miles. Awesome. All right, a hose fills your swimming pool at a rate of 1,000.0 gallons per hour. The question is, how much is this in milliliters per second? So my first question, how many sig figs we got in this number? Yeah, 5. So if we end a number to the right of the decimal with a 0, that 0 is significant. And any zeros that are between significant digits are significant, so they're all significant. We got 5. So our answer should have 5 sig figs. Good times. In this case, our gallons per hour, what do we eventually want to turn this into? Milliliters per second. So we got 2 conversions. This often makes this much more difficult for students. But I need to convert hours to seconds and gallons to milliliters. Which conversion is easier? Yeah, let's turn the hours into seconds. So I'm going to do that first. So in this case, what do I want to convert hours to? Probably go minutes. If you already knew that there were 3,600 seconds in an hour, great. If not, we'd do it right through here. So that's going to get my hours there done. And then minutes to seconds. So, and that'll get take care of my minutes. In this case, 1 hour, 60 minutes. 1 minute is 60 seconds. Or again, you could have combined this all if you knew it and just said 1 hour is the same as 3,600 seconds. But now the gallons part. And in this case, why is this such a bigger pain in the butt here? We're switching over systems yet again. So we need a crossover conversion, and the one provided is that 1 gallon is 3.785 liters. So in this case, we're already ready to convert and cross over. So we'll go gallons to liters, and then liters to finally milliliters, which is where we're headed. Cool, the crossover one is provided. 1 gallon is, again, 3.785 liters. And again, how many sig figs is this really? It looks like 4, but because it's a conversion factor, you should assume it's an infinite number. Awesome. So, and then finally, liters and milliliters. Who gets the 1?
Milliliters.
Yeah, 1, and then milli means 10 to the what?
Milli means 10 to the negative 3.
Awesome, 10 to the minus 3. And again here, I'm relying on your calculator. Cool, and again, what are the units on that?
That would be milliliters per second.
Milliliters per second. Now, how many sig figs are we supposed to end up with here?
5.
5. So we want to go all the way to here. Is that 3 going to round up or round down? Yeah, he's going to round up. So really, we're going to get 1,051.4 milliliters per second. Life is good. You're also going to see this show up in the context of density calculations. So first of all, what's the definition for density?
Density is mass over volume.
Good, mass over volume. And if you recall, whereas mass and volume are extensive properties, density is an intensive property, which means that it doesn't depend on
How much stuff there is.
good, how much stuff there is, the size of your sample. So our first question here says a cube with 2 centimeter edges. Weighs 10.0 grams. What is its density? So density is mass over volume. If we have the mass and the volume, we can solve for density. Which one of those do we already have?
We already have mass.
Good, we already have mass. And what is that mass provided already? Good, 10.0 grams. But we do not have the volume, so we have to figure that out. What's the volume of a cube?
Volume cube is length times width times height.
Good, length times width times height. And if this is a perfect cube, then 2 by 2 by 2, which is? 8. And in this case, 8 what?
Centimeters.
Not just centimeters, because it's centimeters times centimeters times centimeters, which is? Good, centimeters cubed. And in this case, then, density in grams per centimeter cubed would be? 1.25 grams per centimeter cubed. Now, how many sig figs should we end up with here? Oh, and I jacked this, right? Because on your handout, this was 2.00 centimeters.
Okay.
Which,
So 3.
yeah, we got 3 sig figs provided in 10.0 grams, 3 sig figs with the 2.0 centimeters. So we should end up with 3 sig figs, and we've got it. Exactly 1.25 grams per centimeter cubed is 3 sig figs. We're good to go. Cool. The next question on your handout refers to the same problem here. It says, how much would a cube of this same substance with 5.00 centimeter edges weigh? So in this case, what are we actually trying to solve for? Not density in this case. Question's actually how much would this cube of this same substance weigh? So we're actually trying to solve for the mass. If we rearrange here, what's mass actually equal to?
Mass is equal to D times V.
Good, density times volume. So in this case, do we know the density?
Yes.
Why do we know the density?
Because it says of the same substance.
Good, it says of the same substance, and this is an intensive property, and because it doesn't matter if I have a small cube or a big cube, as long as it's the same substance, that intensive property doesn't change. So 1.25 grams per centimeter cubed is our density. And so in this case, we now have 5 centimeter edges, what's our volume now?
125.
Awesome, 5 by 5 by 5, so 125 cubic centimeters. And what is 1.25 times 125? And give me a couple extra sig figs on this. Cool. Cool, so grams. And in this case, how many sig figs should we get properly to end up with an answer here? 3. So we're going to round right here. And do I round up or round down? Down in this case. So 156 grams in the proper sig figs. Sig figs. So we've been doing everything in sig figs. So my question is, when do sig figs matter? When do sig figs matter?
When zeros in between the significant figures are significant.
Well, I don't mean when do zeros matter, but when do sig figs in general? When do you need to worry about these? I mean, all the time. So when you go to the store, you're like, well, it says a gallon, but does that mean 1.0 gallons, 1.00 gallons? You know, what are they saying here? So you're really worried about sig figs always in life? In chemistry mostly. If you're building a bridge, you probably want to worry about sig figs. Things of a sort. If you're in engineering, definitely want to worry about sig figs. So here's the deal. In the lab, you definitely want to worry about sig figs. Your TA is going to care on your lab reports. Make sure you're reporting everything in proper sig figs. On the exams, here's the deal. What kind of tests are you taking?
Chemistry exam.
Chemistry exam, but what's the format? Well, you haven't had one yet, but it's multiple choice. On a multiple choice exam, the only place you're really going to have to worry about sig figs is on a problem that's specifically asking about sig figs. So, which is going to happen on this first exam, maybe on the final exam from this first semester, and never again. So as far as outside of lab, you'll have to worry about it on this first test on a couple of problems, and maybe on the final exam on maybe one problem. And pretty much after that, though, they're not going to give different answer choices except for that type of question that express the same answer in multiple different types of sig figs or numbers of sig figs, only for a couple questions. And so most of the time, this is not going to be a big deal outside of lab. But you definitely want to be aware of it for this first exam. So when are zeros significant and when are they not significant?
Zeros in between two significant figures are,
And where do we see zeros in between sig figs up here?
43.001.
Good. Those zeros are in between significant figures, so they're significant. Great. So zeros in between sig figures are significant.
Zeros to the right of the decimals or at the end are.
Good. To the right of the decimal, when we end with a 0, that 0 is significant. And since that 0 is significant and that 1 is significant, then this 0 is also in between sig figs, so he's significant. Okay, so now when are zeros not significant?
When they're at the end of a number, but it doesn't have a decimal point.
Good. At the end of a number, left of where the decimal would be, but there's no decimal point written. So these guys are all insignificant. Try and make that look a little better. So these zeros are all insignificant. So in this case, also in this case, these are also insignificant. So in both cases, we would call these both placeholders. They're just pushing the number away from the decimal, if you will. So what is the deal with sig figs, though? Why do we even care? Is this just to torture freshmen?
It's to see how accurate and precise your measurement was.
Good, and it's really more concerned with the precision than the accuracy. But how precisely do you really know your measurement? If somebody asked me, how much money is in your bank account? And I said, well, $300. Well, if I look, did I mean exactly 300, or did I have $280 or $282.43, or what is really in my bank account? But maybe I checked online earlier today and I have exactly $300, period. So how well do you know the number you're talking about? That's the big deal with sig figs. Because if you're using a number and you only know it really so precisely, if you use it to determine calculations, it's going to limit how precisely you know what you determine there as well. So in this case, if I look at 43,000 here, I'm saying somewhere around 43,000, and I really only know it to give or take 1,000. Only really know it to the thousandths place all that well. So, the rest of it's kind of guesswork. What if, I was counting ducks on a pond, really populated pond here, and when I counted them, there were exactly 43,000 ducks. I counted them exactly. It wasn't 42,997 or anything like that. It was exactly 43,000 ducks. How would I show that?
You need a decimal point and another zero.
So if you put the decimal point there, it implies that these zeros are significant, in this case, to the left of the decimal. So and we don't need the extra 0 because I didn't measure tenths of ducks. With ducks, and I'm counting ducks, there is no tenths of a duck or anything like that. You don't have to worry about that. But in this case, just that decimal point now implies these are significant as well. And that's a number we know much more precisely than just say 43,000 without that decimal point. Now we know it to the nearest whole number. So with, in this case, counting ducks. If we multiply numbers or divide numbers, how do we decide how many sig figs your answer should have? We kind of already covered this. Whichever is your least significant number, however many sig figs it has, is how many sig figs your answer should have. But what about with addition and subtraction? Usually we think addition and subtraction is easier than multiplication and division, but it's not so much the case. If I wanted to add or subtract these numbers, so in this case, I'm just going to add them up. I'm not really going to add them up, and I'm not going to have you do it with your calculator or anything either. But if we added these, how do I know how many sig figs my answer should have?
How many decimal places you go over?
Yeah. So whatever the least precise of these numbers is, not in total number of sig figs, but to what decimal place we know it to, that's what's going to determine the decimal place for your answer. So in this case, with this number, its most significant digit here is in the what place? Thousands place. And this one, its most significant figure is in the tenths place. And then this one? In the hundredths place. Which one do we know the least precisely? The tenths place. And so our answer should be to the tenths place. Not the thousands, not the hundredths, only to the tenths place. So addition, subtraction, a little bit different than multiplication, division. Cool. That is all I want to say about sig figs.